Welcome back to Wildcat Academy. Today we're going to be talking about exponential growth and decay. In particular, we're going to be modeling applications using exponential functions. Let's go ahead and jump into some examples and talk about it. An exponential function can be modeled with the initial value, a, and that's sub-zero. That means the initial value. That's our starting value, our initial value. So in a word problem, that's going to be whatever our initial population is that we'll be talking about. B is going to be our growth rate. You can talk about this being a growth factor. If it is greater than 1, then it's a growth. If it is between 0 and 1, it's a decay rate. So, but also it's always the growth factor. It's what we're multiplying by in order to change that population. If it's less than 1, then the values are getting smaller, so it's decaying. If the value is greater than 1, that will be increasing. Now, x is the number of periods of growth over, and most of the time that is represented in time, days, weeks, years, hours, minutes, and that can be changed. So know that in a more complex situation that we would have the initial value, we're going to have the growth rate, and we're going to have some time t, and it's going to be divided by the number of how long the period is that it takes that matches this growth rate. So this can be changed and manipulated as you become more comfortable with exponential functions. We can change that the period that we are representing our growth rate in. Today we're going to be given the growth rate, and we're going to match the period that we put here so that our function will be modeled correctly. So let's take a look at a few examples. So if a population of 200 cells doubles every hour, write a function p of t that represents the population after t hours. So again, we're going to be using the idea that we're going to have some initial value as our beginning number right here. And then we're going to have the growth rate, and it's going to be raised to the amount of time. All right. So these are very simple models. Like we don't have the period is 1 hour, so we have division by 1 as our exponent. But our initial value is 200 cells, and then our growth rate is kind of hidden, the fact that it doubles. So it's stated there, but it's not a number represented, so it will double. And it's going to double every hour, and here t is hours, so p of t is equal to 200 times 2 to the t. And example 2 states that the Ebola virus has an infection rate of 12% per day, and there are 3 cases today. Write a function p of d that represents the number of infected patients d after d days. So we will once again take p of d. We'll take our initial value, the number of cases. There are 3 cases currently. That's our initial value. It is growing at a 12% rate. So our growth rate is going to be 1 plus the percentage increase. So that r value that we're growing by. So it's going to be 1 plus 0.12. That changes it to 0.12 or 1.12. So again, that represents the 100% plus the 12%. That's 112% of the original value. So that's 1.12. So we're going to, that's going to be the value that we place in here, 1.12, and after d days. So this will be the function that would model the situation. All right, so let's look at some more complex modeling. So a population of 125 bacteria doubles every 6 days. Write a function p of t that represents the number of bacteria after t days. So we'll write a function p of t. We'll use our initial value of 125 bacteria. Our growth rate comes from the fact that it's doubling, growth factor of 2. And that's happening every 6 days. So we'll take the amount of time t and we will divide it by 6. And that means that after 6 days, 6 divided by 6, that means it will double once. After 12 days, 12 divided by 6, it will have doubled twice. which logically makes sense. So that's the reason we were dividing it by 6 there. The population of 120,000 people is growing at a rate of 1% per 2 months. Write a function p of t that represents the population after t days. So once again, we'll take p of t, we'll take our initial population, which is 120,000. That initial value always just sits out there on the front. That's where it goes. And the growth rate this time is going to be 1 plus, and we're going to convert that percent to 0.01 so that we can have our growth rate correct here. And that is going to grow after 2 months. So take the number of months, divide it by 2, and then we can simplify that down if we want to. 1.01 to the t over 2. So just remember that if you're doing a percentage increase, that you're going to have that 100%, and that's plus the 0.01 that it's increasing. And if it was a percentage decrease, we would do something very similar. If you're giving the growth rate just straight away, then you can just place that in there. Typically with the percentage, there's a little calculation here that you have to do to insert that into our model. In example 5, we're going to be modeling a half-life problem. So the half-life of a radioactive substance is 20 years. Write a function that could determine the amount of 250 milligrams of the substance S of t remaining after t years. So we'll start with the function S of t, and then a half-life problem or a decay problem will always start out the same way that we're doing our growth problems. It's going to start off with the initial amount. The only difference is that our rate of change here is going to be less than 1. So instead of growing, it's going to decay because of that, because we're multiplying by a factor of 1/2 every so many years. So we're going to take the number of years, and the period that we are that our half-life is modeled to is 20 years. So we can see that we have initial value 250. Here is our decay rate 1/2, and then we can see that the half-life matches to 20 years there. All right, so in example 6, Jessica purchases a new car for $24,000. The car will depreciate at a rate of 10% per year. Write an exponential function to model the situation. So the current value of the car, the current price of the car after t years. So we're going to take the initial value of the car, and then we're going to put our decay rate here. And because we are depreciating, we are decreasing the value, we'll take 100%. Remember, this is going to be very similar to our growth, only instead of addition, we're going to be subtracting that R value, percentage. So 1 minus 0.1, because we get the 0.1 from converting 10% to a decimal 0.10. And it happens after t years. That's going to match there. So we're just decreasing 10% per year. So it ends up being 24,000 times 0.9 t. Now with decay problems, with the percentage change like this, it's a little bit harder to see our decay rate. But our decay rate is 10%, and that is just 1 minus 0.9, and that gives us our 0.1 decay rate. That's going to end our video for today. So if you found that video helpful, be sure to hit the like button below. Subscribe to the channel if this is your first time visiting with us so you don't miss out any great videos from Wildcat Academy. And if you have more questions over exponential modeling, please leave a comment below. Be happy to answer those for you.